So here I've plotted out a curve, cos 2t, cos 3t, cos 2t sine 3t, and sine 2t. It's a pretty nifty looking curve. And I've drawn the tangent vectors as before, but I've also drawn the vector from the origin to the point on the curve. Now you can notice that this curve has constant length. So the magnitude of r of t is equal to 1 for all values of t. For us, it doesn't matter that it's exactly 1, it matters that it's a constant. So in other words, the point r of t is always going to be, this curve is being traced out on the unit sphere, the sphere of radius 1. Now something interesting happens, so you can play around with the t values. The position vector, so the vector from the origin to the point on the curve, is always orthogonal to the velocity vector. Now, this isn't a coincidence or just something that happened for this particular curve. In fact, in general, anytime we have a curve with constant length, then the velocity or the position vector in that case will always be orthogonal to the velocity vector. And so this is a nice application of the differentiation rules we just saw. So proof, by assumption, the length of r of t is constant, while the length is the square root of the dot product. So we can rewrite this as r of t dot r of t is c squared. C squared is still a constant. So now we differentiate both sides, and the right-hand side will be 0. But from the product rule for the dot product, the left-hand side is r prime of t dot r of t plus r of t dot r prime of t. So that's equal to 0. But of course, that's just 2r prime t dot r of t. And then we can just divide both sides by 2 to get r prime of t dot r of t is 0. So r of t and r prime of t are orthogonal.